Yeah, Dr. Shen, you can again restart.
So yeah, is the screen sharing? It's still disabled actually. Could just.
Yeah, now you can do. Yeah.
Yeah. All right. Okay. So anyway, so I'll just maybe I think I'll just come to the main point. So what we're going to do is we're going to examine now, homomorphisms from the fundamental group of the complement of the knot to S3, which is your permutation group of three elements, and the symmetric group, basically. And why are we doing this? Well, because S3 is the smallest non-abelian group. If we had to take an abelian group, for instance, if we had to take Z3, for instance, any map which is from this to Z3, it actually can be written as a map, as a composition of maps, first from the fundamental group to Z, that is to its abelianization, and then from Z to that. So it's not going to tell us anything, right? Since it goes via Z, it's not going to tell us anything at all if we put an abelian group over here. So instead, we consider a non-abelian group, so what we can do is that so let's examine this. All right. So what does S3 have? I mean, what are the elements of S3? So on the one hand, you have the identity permutation, and then you have these two, which combined with the identity gives you the subgroup Z mod 3, the cyclic group of 3 elements. And these are the rest, right? These are the other ones. Notice that they have all been separated in their conjugacy classes. So this is one conjugacy class, this is another conjugacy class, and of course the identity is a conjugacy class on its own. This is relevant because the relations are of the type conjugacies, right? I mean, one generator is related with the other by a conjugacy relation. So let's look at this subgroup, right? So that is, we are looking at essentially Z mod 3, right? This is the non-abelian, the abelian subgroup of of S3. Now, if I look at this, so this is what I was talking about, that if you look at pi1 of the complement, it is always related with Z because Z is the abelianization. So this is the quotienting by the commutative subgroup, right? So this is a sort of a natural map from the fundamental group to its abelianization. The abelianization is Z, and it's a easy to prove property of an abelianization. That is that if you're given a map, supposing I take some other abelian group, so let's take Z mod 3 for instance. Okay, so if I take Z mod 3 and if I look at a map from the fundamental group of the complement of the knot to Z mod 3, then there will, given any such map over here, there will always exist a map from Z to Z mod 3, which commutes with this. And so essentially, all such homomorphisms correspond with homomorphisms from Z to Z mod 3. So it's nothing unique to the knot. I mean, if we change the knot to another one, we're not going to get a different set. I mean, they're going to be the same as such, right? I mean, so and another observation which you can make is that since all the generators are related to each other, at least in the case of a knot, since all the generators are related to each other via conjugacies, if one element goes to a particular conjugacy class, all the other elements, all the other generators, sorry, if one generator maps to a conjugacy class, all the other generators have to map to the same conjugacy class. So in other words, even if one element, if theta takes even one element to this, to either 1, 1, 2, 3 or 1, 3, 2, all the others have to be taken to one of these two. In fact, if even one of them has to go to the identity, all the others will have to go to the identity. So what I'm trying to say is that these are the useless homomorphisms. These homomorphisms, so you see, if I want to understand the homomorphisms from the fundamental group of S, of the complement of the knot to S3, I need to know, I can understand them by knowing what the generators are taken to. But now I come to the conclusion that if even one of the generators lies inside this, it maps to something that is inside a subgroup, then all the generators map to those, have to map to those under that particular homomorphism. And that homomorphism is therefore useless for telling apart knots, because when I take one knot or the other knot, the number of such homomorphisms are going to remain the same because they factor via this Z. So therefore, the interesting homomorphisms are the ones that map to this conjugacy class. And so what I need to do is, so take some example, supposing one generator AI goes to 1, 2, the other generator AK also goes to, say, the same element, supposing it goes to the same element, then what is its conjugate going to go to? You see, something which is related by the conjugate. It has to go to 1, 2. You see that? So remember that the relations correspond with crossings in the presentation of the fundamental group. And the observation that we're making over here is that if a relation involves 3 generators, and the observation we're making is that if 2 of the generators go to the same thing, then the third is also forced to go to the same element, right? So that's one observation. The second observation is that supposing one of them goes to 1, 2, but the other one goes to something different. It goes to 1, 3. Well, what is the conjugate of 1, 2 by 1, 3? It's 3, 2 or 2, 3, right? And so what this is saying is that if they go to, if two of the generators which are involved in the same relation, if they go to different generators, then the third one is also going to go to a different generator. Okay, so this gives rise to the useful homomorphisms from pi1 of the complement to the symmetric group to S3, right? How do we so once again, there will be some homomorphisms which send everything to the identity. There will be some homomorphisms which again which go into Z mod Z3 and therefore they again go into Z mod Z3, and therefore they're the same for any knot. So we disregard those ones, right? But then there are the class of homomorphisms that go to this particular conjugacy class, and they can be and then we realize that there are 2 key observations about such homomorphisms. That is that if we send one of these generators to 1, 2, and the other one also to 1, 2, or to the same element in this conjugacy class, then the third one has to be this also sent to that. On the other hand, if 2 of them are different, then the third one also has to be different. It has to be, so what happens is that we can make this definition, and instead of 1, 2, 1, 3, and 2, 3, we can try to be a little fancy and call them red, blue, and green. And so we can make this definition that a 3 coloring on a diagram of a knot is a choice of color for each arc. So we choose red, blue, and green as say 3 colors, so that the arcs meeting at a crossing are all of a different color, or they're all of the same color. right? And now you can see what red, blue, and green are. They are nothing but elements of, they are these elements of S3, which is 1, 2, 1, 3, or 2, 3. So what we're doing is we are making a choice for each arc. We are making a choice of labeling it with either red, blue, or green, if you like, or 1, 2, 1, 3, and 2, 3, in such a way that when the three arcs meet at a crossing, they are either labeled all with the same element, or all three of them have to be labeled with the different elements. And if you do that, then by the discussion that we've already had, you have told me where the generators, which elements the generators are to be mapped to. And therefore, what you've done is you have effectively given me a well-defined homomorphism from the fundamental group to S3. So the number of three colorings is therefore a not invariant. The number of ways you can color a diagram by three colors in such a way, the number of such ways, if you count the number of ways, it is a not invariant. Why? Because each choice corresponds with a homomorphism from the complement of the knot, fundamental group of the complement of the knot, to S3. Right? So there's the useful homomorphisms. As I said, there are more homomorphisms, but those don't tear apart knots, so we keep them aside. And so it corresponds with that. So the number of three colorings in a knot is a not invariant. Now, here's the here's the interesting thing. We have defined a three coloring invariant. We have discovered it by analyzing the fundamental group of the complement of the knot. Right? So what we did was we looked at the fundamental group of the complement of the knot. The first question we asked is, we can represent knots by diagrams. Is there a way to extract the fundamental group from the diagram? And for a moment, we were happy that we could do that. But then we realized that all we got was a presentation of the knot, and these are non-abelian knots in general, and its presentations don't tell us much on their, unless you, I mean, not on their own at least. So what we did was we then decided that we would use the presentation of the knot to analyze the homomorphisms from that knot to a very simple, the simplest non-abelian group, which is S3. And the presentation allowed us to have a simple way to count them, to count the number of homomorphisms. And because of that, and one way of counting them is to make this definition, that is of a coloring of a diagram, and to realize, and therefore, we realize that the coloring of the diagram is independent of the diagram. It actually depends on the knot. So if you have two diagrams, one diagram may have only 3 arcs, the other diagram may have 53 arcs, and they both might represent the same knot. But when we count the number of colors that we get over here, we will find that both those diagrams give you the same coloring if the knots are isotopic to each other, and therefore it's an invariant. Now the interesting thing is that knot theory, when we look at them in terms of diagrams, there is a diagrammatic way to define. So of course, isotopy, when we say the two knots are isotopic, we are saying that there exists an isotopy converting one knot to another. Well, there is a way to convert that into diagrams. And so if we have two diagrams representing two knots, if the two knots are isotopic, there is a theorem which says that the two diagrams can be related by what are called Reidemeister moves. I won't describe them here because they're not going to be too important for my talk. My talk is about the space around knots rather than all these combinatorial methods. But the point is that that these Reidemeister moves are a very they sort of reduce knots to a game of working with, you can work with diagrams, and these Reidemeister moves are discrete, in the sense that when you want to prove that two knots are equivalent, and if you're successful at it, then you do that by providing a sequence of diagrams, a sequence of Reidemeister moves, as they called, which show how one knot converts to the other. And if you suspect that something is an invariant, you can do this by proving that when you perform, there are 3 Reidemeister moves, and any isotopy is a combination of all of these, and you prove that something is an invariant by proving that it's invariant under these 3 Reidemeister moves. And what happens therefore is that this number of 3 colorings, which we did so much of work to discover, now we can completely forget about how we obtained it. And there are lots of texts. If you look for 3 colorings, they'll probably prove it this way. The definition need make no mention of the fundamental group, but even the proof that it's an invariant need not make any mention of the fundamental group at all. You can try it out as an exercise. Try to prove that the 3 coloring, the number of 3 colors remains invariant under the 3 Reidemeister moves. If you look up what Reidemeister moves are and you try to, you will find that it's quite easy to prove. You know, you'll see that the number when you change from one move to the other, all you have to do is to keep a track of, you know, the colorings, how the colorings of the arcs would change, and you would realize that all 3 of them magically give you the same number. And it'll seem like magic when you look at the proof. It's just like, you know, magically it works out. But the reason why it works out is, well, all this. And so, you know, so this is a game one can play with knot theory, which is you could reduce it to, you could discover an invariant in some rather, in a more advanced way. And, but then both the definition and the proof that it is an invariant can use mathematics, which is so simple that you can explain it to a high school student. You know, someone who doesn't even know group theory or doesn't even know, you know, topology. So yeah, but then it appears very mysterious. You know, this sort of tells you why it is, you know, and how it was discovered and why it gives you a better understanding of why it works. Anyway, so that's the 3 coloring invariant. And well, here's the proof. Of course, is quite simple. It's the number of useful homomorphisms to S3. And well, so I think, sorry, this was actually just to, sorry, this is, I should have put somewhere else. Okay, so what have we done right now? Given a knot, we had an invariant fundamental group of the knot. It's hard to compute it. It appears easy, but because of the word problem, it's hard to actually know what that group really is. But then from it, we could extract this thing called the 3 coloring, the number of 3 colors. And we could extract that. It can be pretty complicated. And here, all you're doing is you're counting homomorphisms from that group to S3, which is a very small group anyway. It's a non-abelian quite a small one. So if you, you know, if you, there'll be plenty of groups which will have the same number of homomorphisms to S3. But nevertheless, something's better than nothing. And in fact, it's not just useful as you know, for telling apart knots. It actually can tell us something about properties of knots. So let me give you a brief description of that. So first, I want to tell you something that, I want to tell you that this 3 coloring invariant, you know, when you want to choose, instead of choosing red, blue, and green, if you choose elements of you know, if you choose elements of Z mod 3, so that means you choose 0, 1, and 2. Remember, Z mod 3 is a field. You can apply linear algebra, and you could give a linear algebraic criterion to this. Now, there's a typo over here. This is actually Z mod 3 to the power of n. This is a Cartesian product, Z mod 3 to the power of n. So x1. So each component here belongs to Z mod 3. So what are x1 up to xn? They are the arcs. They label the arcs, and each of these arcs, you know, each of these arcs can be labeled with a color, and a color can, as we saw, is just an element of S3, particularly 1, 2, 2, 1, 2, 3, and 3, 1. But then we could we could, if you know, this condition that there are the colors have to be the same or different can be captured very easily by saying that if we look at you know, these things, the condition that we need is that the sum at each crossing, so supposing xi, xj, and xk are 3 arcs meeting at a crossing, then the sum should be 0 mod 3, right? Notice it takes care of both the conditions. They either have to be the same color. Well, if they're going to be the same color, then it's going to be 3 times that particular number, in which case, and 3 times that number is going to be mod 3 is going to be 0. Or they have to be different. So in other words, one will be 0, one will be 1, one will be 2. 0 plus 1 plus 2 is equal to 3, which is 0 mod 3. The only thing that you have to disallow is 2 of them are the same kind and 1 of them different, and you can check that those are the cases when it's not equal to 0 mod 3. So what happened? Suddenly, this becomes this whole 3 coloring invariant is simply linear algebra. You have this tuple, you have these unknowns for each arc, and each arc can be labeled with an element of 0, 1, or 2, with an element of z mod 3. And the condition should be, right, the condition for each crossing. So each crossing gives rise to an equation. So we have certain number of unknowns given by the arcs, and we have certain number of equations given by the crossings, right? And the equations are always of this type. And so what you need to do is to count the number of, so, you know, notice that the dimension of this is precisely 3 raised to the power of the number of 3 colorings. The reason behind that is because you know, when you look at the number of ways of coloring it, you know, if I take red, blue, and green, and if I interchange those, if I interchange red, blue, and green, I'm still going to be able to do it. It's still going to satisfy the same condition. So that is why it's, you know, there's this 3 to the power of this. Anyway, the point is that counting, you know, we just have to count the number of solutions, and that will tell us the number of 3 colorings, right? So we just have to count the number of solutions, and that's just linear algebra. So what you could do is, given a knot diagram, you could take these, label these as variables, x, x1, x2, etc., and each of these conditions for each crossing will give you a linear equation. And so you have those linear equations.
Am I audible?
Yeah, you are.
So this set is basically you are summing 3 things from the n things, right?
But there's not just one relation. There are actually one for each crossing. There are many relations.
One for each crossing. Okay.
Because for each crossing, we have to ensure. So we have to ensure that the xi's are numbered by 0, 1, or 3, 0, 1, or 2, in such a way that whenever the arcs meet a crossing, they should all be of the same color or different color, which in other words means that for each crossing, the sum should be 0.
Okay.
So there are multiple equations and
multiple equations.
Right. Yeah.
Okay.
So and so you're counting the number of solutions. Yeah. So the way to do this is, of course, your usual linear algebra. What you could do is you could create a matrix out of it, right? Representing where each row represents the equation, and each of these equations that it has to satisfy. Sorry, this is not typeset very well. I think the braces are missing. This should be a set, and also there are multiple equations, and then you can reduce that. You know, you can use Gaussian elimination, etc., and reduce that matrix, and then use that to figure out the nullity, and you know, that way you'll get the number of solutions, etc. The point is that now everything is reduced to linear algebra, and in fact, you can use this to prove the following theorem, which is not really hard to prove actually. And what it says is that if you look at the unknotting number, now let me just briefly describe what the unknotting number is. It's a much more natural property of a knot. It's also sometimes called an invariant of a knot, but I don't want to use that term because it's not used to tell apart knots. Strictly speaking, it is an invariant, but it's defined so that it has to be invariant anyway. So the unknotting number is defined in the following way. So what you do is you ask, given a knot diagram. So first you define the unknotting number for the diagram. And what is that? Given a knot diagram, what are the least number of crossing switches you need to make? That means you take an under crossing here and make it an over crossing. So, you push this arc down so that the bottom arc now comes up. And you will notice in the case of the trefoil, if you try to imagine it a bit, if I do that, then the trefoil becomes the unknot. Okay. So given a diagram, given a knot diagram, you can define the unknotting number of the diagram to be what is the minimum number of crossing changes you need to make in order to make that a diagram of an unknot. And then what you do is you look at all possible knot diagrams. Okay, that's why it's only theoretically. It's not easy to compute it, because what you have to do is you theoretically define it as you look at all possible diagrams of the given knot and take the minimal unknotting number of of all the possible diagrams over all the possible diagrams, and that is the unknotting number of the knot. So if a knot has unknotting number 1, it means there exists some diagram of the knot, so that when you make one single crossing change to that diagram, it becomes the unknot. Now it's easy to therefore see that you can always get a bound on the unknotting number, in the sense that supposing you have a particular diagram, then its unknotting number is, of course, an upper bound for the unknotting number, because we don't know whether a simpler diagram actually exists out of all the infinite possibilities. So given an example, supposing I give you a diagram and you know that its unknotting number is, say, 2 of that particular diagram, then you know that the actual unknotting number is no bigger than 2. But you don't know whether there exists a diagram which has a smaller unknotting number than 2. That can be very hard, as you can imagine, because there are infinitely many diagrams, and it can be very difficult to prove it in general. However, here we get a partial answer. What we can prove is that the unknotting number is bounded below by, the number of colorings. Oh, actually, sorry. It's basically bounded below by log 3 of the dimension. So basically, what we want is the power. So I shouldn't use the log 3 over here. It's just the power over here. But the point is that you always get an upper bound on the unknotting number if you're given a particular diagram, right? Whatever diagram you have at hand. But now you get a lower bound. And so that's better, because if you have a diagram, and let's say you compute this lower, so this lower bound can be computed using any diagram, because you use any diagram, you compute the number of free colorings, and you try to figure out this particular thing, and you try to figure out the lower bound. And if it so happens that you find a diagram whose unknotting number matches with the lower bound, then you're done. You know that for that particular knot, this is the unknotting number. Okay, so I'm not going to do the proof over here. It's actually a very simple combinatorial proof. This is in this book. There's a tilde over here, which is not, it might be simpler for you to actually just scan this. This will be on the screen for some time. So you can scan the QR code. It'll take you to the website. Okay, so this by the way, this set of notes is quite a good set of notes on combinatorial knot theory, and it introduces and it proves this theorem, and in fact it also I think does the 3 coloring from the perspective of the knot group, etc. Anyway, now I want to come to the other important part, which is the Alexander polynomial. So let's come back to our I told you that the pessimistic way of looking at the fundamental group of the knot complement is that its abelianization is always Z, irrespective of what the knot is. However, the optimistic way is to ask, what does that tell me about the space of what does it tell me about the space around the knot K? Here's an interesting property that the space around knots have, and that is the following: that if you look at the commutative subgroup of the knot, notice that and you consider the cover associated with the commutative subgroup. So I'll use either C or the commutative of this should be G comma G actually. Sorry, I don't know why I call it, but I'll use this notation. Sorry, this I'll use C to denote this, the commutator subgroup. And if you consider the cover associated with this, so let me remind you that for every subgroup of the fundamental group of a topological space, there is a cover associated with it. And there is a deck transformation group of the cover. Now notice that the deck transformation group of this particular cover, well, the deck transformation group is always isomorphic to the quotient of the subgroup that is associated with that cover. So the deck transformation group in this case will have to be Z, right? But also notice that if I take any other cover whose deck transformation group is also abelian, then the subgroup that it is associated with has to be such that G mod H is abelian, because G mod H, so as you know, there's this Galois correspondence between subgroups and covers, and if and also the deck transformation group of the group of covering transformations of a cover is isomorphic to the quotient of the corresponding group subgroup, right? A quotient by that. And so what will happen is, so since this has to be abelian, the only way this can be abelian is if this subgroup that you're quotienting by is big enough to contain the entire commutator subgroup. And because of that, if you look at any other cover which is a deck transformation, whose deck transformation is abelian, it will be covered by X tilde. This should be an X tilde, sorry. This is X tilde. There's a typo over here. So it has to be covered by X tilde. Anyway, what I'm trying to say is that corresponding to the commutator subgroup, there is this cover whose deck transformation group is abelian, but that's a very special cover, because if you take any other cover of the complement of the knot and you find that its deck transformation group is abelian, it has to be covered by X tilde. Okay, it has to be covered by X tilde. So this is called so another way of saying this is that the universal abelian cover of the complement of a knot is always cyclic. And we say a cover is cyclic if its deck transformation group is cyclic. So the universal abelian cover is always cyclic, and it's Z. It's infinite cyclic, in fact. So it's always Z. So it's called universal because if you have any other cover whose deck transformation group is abelian, it has to be covered by this one, by this X tilde. Okay. So so that's something special about knot complements, right? About the topology, which is that they have this special cover, this special abelian cover. In other words, abelian cover means that the deck transformation group is abelian, which covers all possible abelian covers. And not only that, this special abelian cover, in the case of the complement of the knot, its deck transformation group is as simple as just Z. It's not just any other abelian group. It is just Z. And so, well, let's study it. Let's study that instead. And we can actually study. So as I told you, the homology, the first homology. So here, so in fact, I already told you that the first homology of the complement of the knot is always going to be Z. There's another reason for it. The reason for it is, as you might know, that the first homology is the abelianization of the fundamental group of a space. So, and we've already seen that the fundamental group, the abelianization is always Z in the case of the complement of the knot. So the homology of the complement of a knot is again a completely useless invariant because it is always Z. However, instead of taking the homology of S3 minus K, why don't we take the homology of X tilde, which is the universal abelian cover of S3 minus K? And you will see why we chose this among all possible covers. One could have asked, why not choose some other covers? Obviously, we won't choose we will never choose the universal cover because it's simply connected, and therefore its homology will be trivial. So but we have the special cover here, thanks to the fundamental, the abelianization of G always being Z. And so we can compute the homology of that. But we have another advantage. Remember that the deck transformation group is Z, right? And therefore it can be generated by
Sorry for
one.
interrupting you,
Yeah,
sir.
sorry.
Sorry for interrupting you. The meeting time is this like 2 minutes. So can we have a 5-minute break and join after that?
Yeah, sure. All right.
I request participant to join the meet like after 5 minutes.
Right.
The link would be the same.